Okay, so as usual, please request anyone who can turn on your camera. That would be very helpful and make their, both experience for you and me more lively. So please do so. This is a relatively small class, so I hope it will be interactive. I'm just waiting a few more people, hopefully, to join before we start. Any questions about tutorial so far, about the assignment? I think Bojan was handling questions on Piazza very well. Every time I go and check there, all the questions already answered, so I didn't have a chance to answer any questions so far, which is a good indication usually. So if there are any issues, you can leave questions on Piazza as usual, or you can ask me. Again, I remind everyone, so since this is relatively small class, so you can use chat to ask questions, but you can also raise your hand, or you can use your voice to just unmute yourself and ask questions. Let me change the grid so I can see more people. Okay, so let's start. So today we're going to talk mostly about data flow analysis, but that's major part, probably 2/3 or 3/4 of today's lecture. But first I want to start with a little bit of refresher from the last lecture. So we talk a lot about organizational stuff, but I'll obviously focus on technical things. So there are certain things I really want you to remember that's really important in any compiler going to use. One topic we covered well on value numbering, we just were about. I'll go over that again. Okay, so basic block formations. Remember, basic block is a key structural element of intermediate representation within any compiler. So this is not part of the code. Remember, this is a part of the intermediate representation that help analysis. You will see in pretty much anything we're going to do, the first step we start is we say, let's look at the control flow graph, right? So it's relatively straightforward to build. I just remind you, right? So you start with a plain code that has all the usual statements. It has, branches. It has go-to operators. So the first step we do, we identify the leader of each basic block. So essentially the leaders can be either first instructions, any target of a jump, and any instruction immediately following a jump, the jump that is not unconditional. What does that mean? It means that essentially those are the only possible places for the basic block to start. Then basic block starts at the leader instruction. So after you found the leader instructions, you already know where to start looking, and ends at the instruction immediately before another leader, or if it's a last instruction. So we did this example last time. I'll just show you yet again that a piece of code from the textbook. This is how the control flow graph would look like. So it's a relatively straightforward process. You just go linearly through the code, you find some branches, you mark instructions accordingly, and then you get your basic blocks, and then you get some edges here. There are a lot of fall through edges, obviously, right? If this is a target of some branch that happens to be a block, but there can be a possibility to fall through. So there is always an edge here, unless there is an unconditional branch, okay? This is just a reminder from the previous class. None of that should be new to you. As a part of your home assignment 1, you will build some of the control flows as well. It's relatively straightforward for small graphs, but it's a very critical graph for any serious analysis. After that, we started to talk about data flow analysis, initial data flow analysis, and I give you an examples of 2 abstractions. And the first abstractions, the some we had time to cover, that seemed to look okay, but it turned to be not very good. Again, this is the reminder from the last class. So this is essentially directed acyclic graph used to represent the expression. This is nothing new. You've seen this before in the previous class. And we've shown that this expression can be successfully represented in this form. But essentially, and that's how it's going to be stored, how you generate and optimize codes. The problem is that abstraction, even though it works for this expression, might not work for statements. So this abstraction might work in one case, but not in another case in terms of applications. So the question to you here is, given this code, 4 lines of code, A equals B plus C, B equals A minus D, C equals B plus C, and D equals A minus D. This is what the DAG would generate as the intermediate representation. And based on that, it would propose this optimized code. The question to you, is this correct or not? If you have an opinion, please just mute yourself or post a chat message if you prefer this way. Both ways work for me. So any opinions if that's, so this is just your input. This is representation. You can just trust it. Trust me, this is how DAG will do it. It's just very straightforward. It sees, for example, B plus C, right? So it does B plus C, that becomes an A, right? And then you had A minus D, right? And then A minus D is twice. So it has two values, B and D in that node. And then you had another value C that's used here. So that's the representation that's going to happen. Any opinions? Is this the right thing to do or not?
I think in the end, so in the original code, B was changed, but then in the optimized code, B still stays the same.
Yeah, you're absolutely correct. So essentially, this representation, unfortunately, if you do it for statements, doesn't detect the dynamics of the value, because that's a symbolic representation. It treats B the same because it sees this as an expression. It sees B plus C as another regular expression of B plus C. It doesn't have a notion of temporal assignment of the value, so the B can be different here and here. So this is a limitation of this representation that, if applied blindly to statements, would generate wrong code. So this optimized code is actually incorrect and would lead to wrong results. You can try the values and you will see it, right? And mostly because it's reusing B plus C here and here, but in two places, but in reality, it's actually wrong. So, okay. So that's the problem with DAGs. And that's why they're not used for certain optimizations, like open expression elimination, because it's actually incorrect representation. It doesn't mean that DAGs are bad. It just means they had a limited use case. So this is a brief summary about those issues that we just summarized. So it's it doesn't detect the time aspect of the assignment. And the way to solve the problem is to build a graph in order of execution and attach variable name to the latest value. So the proposal based on that is called value numbering. It's a very powerful algorithm. It's used in the basic blocks all over the place. It's a very simple idea. So essentially, it's an explicit way to represent both values and time at the same time. What does it mean? It means that for every static variable, I assigned a dynamic value depending where it happens. So the same variable might be assigned to the same value if that variable didn't change, or if over time the value changed, it might assign to a different dynamic value. Okay, so that's what this graph means. So the way it's implemented is a simple hash table. Each value essentially has its own number, and the common sub-expression means the same value number. So essentially, we create an array or a table called variable to value that has a mapping of every variable as you go through the code. And that mapping used to determine the value that represent the expressions. So we first map variables into values, and then by looking at those dynamic values and looking at the mapping, we can say whether that R1 plus R2 are really the same or not, because we know the precise encodings. right? So essentially the idea, and I'll show you an example later on. So essentially the idea that having that, we can have a very simple algorithm that I'll just briefly go over here for you. So, and I'll only cover the binary instructions here for simplicity. So what we do, we have that special tables for variables, right? That we can have expressions that has a binary operator op and two value numbers as an input. And then essentially what we do, if I had a variable, like if I had an instruction with two operands, source 1 and source 2, that do an operation op, like plus, minus, or multiplication, and a destination register DST, what we do, we get the number from the table assigned to register 1 or value 1, then the value assigned for register 2. And then we're gonna get a search whether we already have a registered expression that has these as first parameters, these as a second parameter, and doing operation op. If that's already an active value for that, then instead of having that expression computed again, we just replace it with a copy instruction that would take the value we already have from that array for that specific variable, and we have a copy instructions. So essentially we had a plus b, and we know that a is r1 and b is r2. We can just replace it with r1 plus r2, value of that was already stored. If you don't find it, which is the common case at the beginning, then you're gonna create a new entry into this structure. And so you would create a new temporary variable, TV, right? And then you replace the value you've seen with the actual assignment, right? TV, and it's a register T1 or T2 that equals to values like access here, operand, second operand. So if that was a plus b, that was going to be what a maps to, like R1 plus R2, and that's assigned to register, say, T3. And then you had a copy destination register that might have been R2, you copy T3 into it, and then you store it. So essentially for every expression we see, we either reuse it based on the table we already have, or we create that new expression, put it in the code, and then next time we see it, we can be reused. This is a very simple description of the algorithm, simplified. I keep it here mostly for you for your convenience. When you're going to look at home, you can run through the algorithm. Let me show you how it works in practice. So first questions you might ask, what are the initial values of the variables? So those are essentially values that are available at the beginning of the basic blocks. So there are many possible implementations of that. That you can do that I'm not going to discuss here. The real implementation of the values and where two value arrays are like they're done as hash tables. That's the most efficient way. So let me just show you a piece of code on how we're going to get something like that done with value numbering. So remember, this is the piece of code we have as an input, similarly to you've seen before, right? Remember the one that didn't work with DAGs, right? You still remember that, right? I hope. Any questions so far? Hope I'm not too fast. So remember the same thing. A equals B plus C, B equals A minus D, C equals B plus C, remember, different B, and D equals A minus D. So what's going to happen, A, B, and C are some variables that needs an assignment to intermediate registers or virtual registers. So we just assign them one by one. At the beginning, A is assigned to R1, B get assignment R2, C R3, D R4. Because we assume that at the beginning of the basic block, those values have meaning, right? Because that's all part of one basic block. There's no branches here. So this is the initial state in our table. So what we do next, we just follow the algorithm. We'll see the expression statement A equals B plus C. So what we do, we look at B plus C as an expression. B means R2, right? C means R3, and the operand is plus. We look at our table, right? And we've never seen R2 plus R3 before. So based on this algorithm, we need to generate two instructions. We generate instruction T1, one because there was not a single expression before, that's the first expression. So it gives us number 1 as the expression and temporal variable T. And we store R2 plus R3 in T1 because the operand is at. And then we copy R1 into T1, right? So how about next line? The next line is still very similar. We had an operand minus, B equals A minus D. We never seen A minus D before. A stands for R1, D stands for R4, right? And then we just had a sub instruction here into a new variable T2 and copy R2 to T2 because that's what it has here, right? Okay. Then when it becomes interesting, when we see B plus C again, what happens? What do we see from our intermediate state? Well, I'll give you a hint. The problem is now B is different, right? The problem is that before I had an expression that represented a D as R2 plus R3, right? But now B has a different meaning, right? Because it was already used in this calculation, right? So when I see R2 plus, so when I see B plus C, I see that that's not the same expression than I've seen before, right? Because I already updated my data structure because the B value was updated, right? It's now equal to T2, right? So because of that, I need to regenerate this expression again, right? Because that, so essentially here, this value numbering structure, the value tables allow me to see that that expression was not happening before, right? Because we update this set variable to value to a new destination. So essentially the key advantage here is when I see the UB plus C, I know it's not the same B plus C, right? Because B is different, okay? Because of that, we're gonna have there the new assignment, okay? So this is the key distinction between this algorithm and what we used before in DAX. So it has a temporal component in the assignment, so it can distinguish between different versions of the variables that has the same representation as a, as a lexicographical representation, right? Because it has a different number associated with this variable. And that allows us to distinguish one from another, and that can help us to avoid some redundancy in the code. Okay, so the value numbering, the beauty of it, it's a relatively simple algorithm, and it's linear in complexity, right? As you can see, everything can be done linearly, line by line. There's no like complicated, computing. So this allows to actually for very efficient implementation for basic blocks and the simple value numbering used in existing compilers even within a basic block. Any questions? So the hand is asking, what is the purpose of copy? The purpose of copy is to distinguish between the temporal variable the algorithm creates versus a permanent registers you map to. If you just bypass that you won't see this. Later on, you might think it's a redundant, but in some cases it's not. So what's going to happen later on, there's going to be a different pass in the compiler that's called copy propagation. So all the redundant copies will be removed. At the end of the day, remember the copy, in most cases, this is just renaming a register from one into another. So at the end of the day, most of the copies are deleted, and they are all, when you actually move virtual registers into some real registers, physical register, that's what it has cost. Right now, copy has no cost, right? It's just, a convenience. So because in some cases, you want to distinguish between the two variables. Okay, so in this simple case, most copies can go away, right, later on. But in some cases it's not, so that's why it's a convenient for the algorithm to generate an independent instruction with its own variable, right? Questions? So this temporal register is essentially like a hashes that you use to distinguish the values. If you look at this code, you see that this expression R2 plus 3 is equals to T1, and this one is equals to T3. They're two different ones, two different entities, right? So you can distinguish, because the beauty of it, if you actually have to reuse B plus C, you know that you need to reuse T3, right? Other than T1 later on.
So question, so if there's no B equals to A minus D, then the next instruction C equals to B plus C will be replaced by just a copy. Is that true?
Absolutely correct. Yep. Yeah.
Okay.
But here we can distinguish one from another, right? And that helps us, right? So we can distinguish one from another. Okay, that's why we need temporary variables. And remember, like, the copy looks like an extra instruction, but in reality, most of this extra instruction would be later removed. What is the difference between this and LLVM-IR? Very good questions. Essentially, as you can see here, so this is, you see the modified assignment, right? You see I can, I didn't finish that. Let me just show that and I'll answer the questions about LLVM-IR. So as you can see, this code and this code, it's because you can, you know, look at the value numbering, you can find that the value of T2 already has exactly the same expression, right? So if you look here, right, R1, and this one, when we're gonna extract the representation, you'll find that this is identical to this one. So this is just the code we're gonna synthesize, but this is what's gonna happen after copy propagation, right? Sorry, not copy propagation, value numbering. So the last statements subtract will be deleted, right? Optimized out. So this is the code you're gonna get after you just generate code by, say, LLVM front end, just line by line, right? And this is what you're gonna get after value numbering.
Sorry, shouldn't that be copy R4 is equal to T2?
Check. Yep, sorry, that's my bad. So this should be R4 here. Thanks, my typo. Any other questions? So coming back, what's the difference between this LLVM-IR? So actually, you're gonna see that LLVM belongs to the class of relatively new compilers. So several things that were on optimizations for old compilers like GCC actually become a part of LLVM. So LLVM-IR actually has some form of LLVM value numbering integrated into its IR. So it actually happens automatically, right? So you're gonna see this also when we're gonna learn SSA representation, they're also part of the IR. So remember, LLVM, this is not a basic compiler, it's a very advanced compiler. So some of this concept already part of the, you know, the compiler. And a lot of optimizations actually that we learned with you already part of LLVM, right? So don't be surprised by that. But right now I'm just showing you why those algorithms and ideas exist to begin with. Does it answer your question, Zihan? Okay, so let's move to the next slide. So that finishes the large, big piece of the previous lecture. And that kind of talks about, you know, This actually tells us a little bit about what we can do in terms of data flow within a single basic block, but that's still quite primitive. So what we want to do next is actually trying to do, you know, equivalent optimizations to what we just did for sub-expressions, origin definitions, or liveness analysis across the full control flow, which obviously has branches, which means there can be some complications of multiple different definitions, right? Or variables available at the same time. So this is what we're going to talk pretty much the whole of today's lecture and substantial part of the next class as well. So today we're going to mostly talk about the structure of the data flow analysis. I'll try to explain you why data flow analysis is useful and needed. You're going to actually see that all compilers have this one way or another, not necessarily done it exactly the way I show it here, but definitely this is the most basic features that any compiler optimizer needs to know about the values. We're going to go over two examples today, origin definitions and liveness analysis. And then, depending how much time we have, I might start the topic on generalizing it, or we might have to do it in the next class. Okay, this is just a quick summary of what to expect next. So what is data flow analysis? So you already have seen local analysis like value numbering. This analyzes the effect of each instructions on their values and registers. It has a composed effects of instructions to derive information from the beginning of the block and all the way instruction by instruction until the end of the block. That's what the value numbering does. So what the data flow tries to achieve, it tries to analyze the fact of each basic block individually and then compose the effects of basic blocks to derive some common information for the basic block boundaries. And from the basic block boundaries, we can again apply local techniques, local analysis like value numbers to generate information on instructions. So the idea, this is a divide and conquer approach, right? I cannot look at the whole program. It's difficult because it's hard to understand which values are equal what at each stage. So we devise a mechanism where we take the graph, break it into control flow. Then within each block, we have local analysis, the ones I demonstrate you just now, value numbering or anything equivalent. And then I compose the information between the blocks by using the branches and looking which values goes in which direction. This at high level what the data flow analysis try to do. It's trying to get local information per block, combine it between the different blocks, and then propagate this information through the blocks, instruction by instructions. That's what it has at high level. Any questions? I'm going to show some examples soon. Okay. So data flow analysis can have different level of precision depending on which information it uses. It can be flow sensitive. It means it takes into account the flow, the control flow within a function. It can be intra-procedural. It can have all the different complications. The example optimization that use data flow are constant propagation. For example, if you had something like copy R2 to 3, copy 3 into R2, right? And if you know that that's the only definition of R2 within this basic block, you can replace R2 with the constants everywhere in this basic block, right? Another example, obviously common sub-expression elimination. Obviously, if I do A plus B and there's another A plus B that was already computed, I don't want to do it again and again. So I want to remove the redundant computation. Another example is that code elimination. If that code never reaches anything useful and it never actually synthesizes anything, it can be just deleted. So this is all examples among just few representative examples you're going to see in this course on where data flow analysis is useful. So let's look at some examples here, right? So this is a typical graph that happens in the programs we write. So some example for people, why would I get a shape like that? What would, so this graph is missing some instructions that are irrelevant for the discussions, but what could generate a control flow like that? Question to you. It's a simple question, yeah.
Maybe a conditional.
Yeah, so if an if statement, So in if statement, if, else, and then after everything converges at the end of the if, that the control flow converges back and we continue the main execution. That's really if else statement, right? I hope all of you understand, you already practiced some. So I just omitted the conditions because they're relevant here for the purposes of what we're going to do with data flow analysis. So what we want to do here is for each variable x, we want to determine the value of x at any point of time. Then which definition defines x? So what does that mean? Well, for example, let's say I had a variable b here, right? I want to know which definition of b is reaching here. Or this is easy here because that's the only part that goes here. B was some value there, so whatever was there still stays the same. But there might be more tricky examples. Imagine you have a value a here, right? Which definition defines a? Well, you can see one definition for 3, another equals b plus c. So the question to you, which definition defines a really?
The last executed one, so 243.
It's a tricky question, Shant. So the thing is, how do you know which one was the last? Was that really the last? Well, if I go that path, that's the last. But what if I go this path? Then it's not the last. So this is where the complication happens. It might be totally possible that the value x might have multiple possible definitions at any point of time. So it means that it's not a trivial, it's not that you always have just one value available, one expression, right? This is why this analysis is important, right? And even a simple trivial control flow like that already causes some challenges, as you can see. Another example, is definition still meaningful alive across this point? Because, for example, this definition can be live on this edge, but be dead along this edge because it was overwritten with this definition, right? So all of that, you know, an important things to take in consideration. So this is, right now, I'm not just even showing you examples of what we're going to do with data flow. I'm just showing you the need for it and why it have some interesting, meaningful information. Another important example, there is a static versus dynamic program representation. So statically, the program is represented as a piece of code, a finite program. And that is just like multiple lines of, say, C code or some intermediate IR, doesn't really matter. So it's all finite and simple, but it can have infinitely many possible execution paths, right? Because I can take all these different branches. I might be sensitive to the input information. So all that can cause me, you know, gazillions of different dynamic paths. So I cannot deal with that complexity in some, you know, trivial way. So the way, without losing some information. So what the data flow analysis does, it comes up with an abstraction that simplifies this dynamic complexity. So we don't try to conceive every possible conceivable path, right? So instead of that, because imagine if you would want to know what the, say, A equals here, and you want to consider any possible control flow in any possible order. That's a nightmare. It's an exponential explosion, right, of possible paths. So what data flow analysis usually goes, it goes for a more simple representation. Its abstraction is we combine the information about all instances at the same program point, right? So essentially, we just assume that anything that could have happened has happened here. So essentially, if there is a path that can lead to the value being A equal 10, then it is possible, right? So that's essentially, so if we cannot prove that that branch is always taken and we never like go through this path, then we have to assume it's possible. So it's essentially data flow analysis abstraction is already conservative. That's what I want from the design point, because the absolutely precise dynamic information is usually infeasible. It's too complicated. So the data flow usually is used by asking the questions like, which definitions define the values using the statement B equals A? So which A means, like, if I want to assign B something, what A can be there? So those are the questions we want to ask of our data flow analysis. Okay, any questions so far? So data flow, so I was asking, so data flow analysis is like doing static analysis without depending on the running environments. I would say more precisely, it's more like collapsing the information of all possible dynamic running environments into one bit of information. So if in one environment, that would be one value, and in another, it's another value, their representation, the abstraction would be to have both possible values as a representation. So it can be one path that leads to that, and another combination of run read to another value. Both has to be stored, right, as a possibility. It's essentially taking one huge dimensions across all possible control flow paths and all possible inputs and collapse them into one like array of possible values. So it might be that any point and any dynamic execution, you either A is equals 10 or either equals 11, and it can only be one possibility, but we're going to fuse both together in order to make it tractable. Does it answer your question? Okay, so the first thing we want to go through is the basic block. Why? Because it's an integral part of our control flow and it's the easiest to deal with. So the building blocks of a basic block are statements, right? The block consists of just a sequence of statements. So if we have a statement of A equals B plus C, what does it do for us? Well, what we know, it have two uses of B and C. So that's the first information. That's the fact of a statement. Another thing we know that A equals B plus C kills an old definition of A. Whatever A was before, I don't care. Now there is a new definition in this basic block. And everything goes below the statement in this basic block should use the new definition, not the old definition. And A here in the statement defines this new definition of A. Okay, that's what a single statement does for uses and definitions and the kill sets. So then we can compose effects of individual statement into something that's called effect of a basic block. How do we do it? Well, we defined a term called a locally exposed use in a basic block. I would, to save time in writing, I would just use BB as a basic block. So a locally exposed use in a basic block is a use of a data item which is not preceded in the basic block by definition of the data item. So for example, it's something that was not overwritten it, that it means that the use is possible. Any definition of a data item in the basic block kills all definition of the same data item reaching the basic block. So I have A equals B plus C, then I have A equal 10, then I have A equal 11 within the same basic block. From the external perspective outside of the basic block, only the last definition matters because that definition is what's visible at the end of the basic block, right? Everything else is being killed within the basic block. It doesn't mean that those definitions are useless, because within the basic block, they can be consumed, right, as an intermediate values. But overall, those values will be not visible outside of the basic block. So a locally available definition is the last definition of the data item in a basic block. So this is the definition that's locally available outside of the basic block. Okay. So let's look at the piece of code here. So remember that a locally available definition is the last definition of an item in a basic block. So let's look at, do you guys see any locally exposed uses in the first line? Remember, that's the definitions of the locally exposed uses. Is a use of a data item which is not preceded by a definition of this data item in this basic block. So do you see any uses in the first line? Locally exposed uses?
Would it be both R1 and R2?
That's correct. check. It's R1, but is it R2? In a basic block is a use of a data item which is not preceded in the basic block by a definition of the data item. So it's R1 and R2. So does it kills any definitions? So for example, any other definitions of T2 would be killed by this statement, okay? Because it overrides T2. What kind of locally available definitions we have at the end of these blocks? Do we have T2? That's one example, right? That's a locally available definition, T2, right? So it's available at the end of this block because it was not redefined. It's not the only one, but it's one example of it, okay? Okay, this is the way how we'll look at the effects of the basic block, right? So it's relatively straightforward, right? It just follows the definition, and it's just a meaningful definition because from the external perspective, the only thing I care is what's the last thing I've seen, right? So any other intermediate values I've seen doesn't really matter. Like, for example, R2 has this R1 plus R2, but then it was redefined by T3, which is R1 multiplied by R1. Only that matters, the last definition. Okay, T3. Okay, this allows us to reason about the basic block. Okay, there's a question here. Will it kill the old definition and generate a new definition if we define and redefine in the same basic block? So essentially, within a basic block, it's exactly that what happens. Every time I see a statement, it kills the definition available at that line, right? This line of the code within this basic block and redefines it into a new one. So if there is something in between that uses this variable, it has to use old definition, and everything that passes after the new definition have to use the new definition. From the external perspective, what we care about is what's available towards the end of the basic block. Because when you do any analysis within the basic block, it's very simple. You just go linearly through the block. At any point of time, you know what each value look like. It's either what I have as an input of my block and what is the latest, and freshest definition of the variable. So that question is easy to answer. What's harder is what's true across different basic blocks. So that's what we're trying to define now. Okay. So let's look at the problem in a little bit more complicated case. So we already learned how to look at different things, but what within a basic block, but how outside of the basic block. So let's say I have 3 basic blocks for simplicity, B1, B2, B3, and it has statements. I numbered the statement, called them D0, D1, D2, D3, D4, D5, D6. Remember, this is just annotations for the ease of argument, right? Those are not part of the code. This is just their, think about the labels, but not part of the code. So what we want, so that I can tell you which line I'm talking about. So you can ask the question like whether D1 reaches this point. So for example, and the point can be here, 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 anyway, beginning of the basic block. This is a question I might be willing to ask using the data flow analysis, whether the definition D1 is available at any point in the program they care about. Remember that every assignment is a definition, and a different D reaches a point P if there exists a path, right? A path from the point immediately following D to P such that D is not killed, which means overwritten along that path. What does that mean? It means that there is it means that it shouldn't be exclusively one. If there is at least some path that leads to that, it means that D1 reaches this point. So let's check this thing with you. The problem formulation using this definition is then For each point of the program, each point, any statement, determine if each definition in the program reaches this point. And that's, as you can imagine, it's a large vector. It's a bit vector to program point that has all possible definitions, right? And for each of them, it says reaches or doesn't reach, right? So for example, here, I already numbered you all the definitions. So how many definitions we have here? The total for the whole graph.
6,
7.
7, 7.
7, yeah. So it means that if I want to have this problem formulation, that at each line of my code, I have a bit vector, a length of 7, that for each of this definition says it can reach its point or it cannot reach this point. So it's either 0 or 1, right? This is essentially what we are storing. Okay, so, and similarly, you can ask whether D1 reaches it. But let's play this game a little bit. Let's try and see whether you can find it. So, for example, let's say at this point of the program, at the beginning of the base, before D5, I want to ask, is D1 reaches this point or not? Should it be 1 or 0 for these positions in this vector?
It should be 1.
Okay.
Because Z is assigned X.
Yeah, and it happens later. That doesn't really matter. It's at the beginning, just before D5. So essentially at this point, if I would have to write this vector, I would, the first component of this vector would be D0. D0, would it reach this point or not?
No, it wouldn't,
Yeah.
because it's killed along the way.
Exactly. So no matter which path we take, this is always overwritten. So it would be 0, and then it would be 1, and so on. And you can keep writing this vector, right? So, and you can do this at any point of time. Which place would be interesting? So this place would be interesting. If I would ask you this question here, oops. If I ask you at this point, D1, does it reach this point or not?
No.
Why not?
Because D6 overwritten X value.
That's true, but that's not enough.
Because it's overwritten in both paths.
Thanks, Zipkin. Yes. So what's important is not just that it's overwritten here, it's overwritten on both paths. So D1 doesn't reach this point neither if I go this way or that way. It's always overwritten, right? Okay, this will just help you to get a feeling of the complexity of the problem, right? Okay, how about D2? So, and same question. For this point, for D2. Would D2 reach this point or not?
Depends on which path it goes through, I guess.
Yeah, but we don't have in our representation such thing like if this path. So the answer is either yes or no. So I'm intentionally teasing you. So like, remember, our representation is not that smart. There can be hundreds of those branches before. So we only had one way to answer this question.
Yes, it reaches the path.
Yeah, remember, thanks, Frank. So essentially, remember the formulation, if there exists a path, so if there's a possibility that reach, then it's possible, right? Okay, so that means that if we look at D2, we would have to say that at this point, D2 could reach this, even though along, along this path, it might be overwritten. But I don't know whether this branch is taken or not. I have to assume that statically it might take any positions, right? And then I had to assume, yeah. Auli is saying taking the union of branches, more or less, yes. We're going to define the problem soon, and you're going to get a union is going to play a role here. Yes, you're going to look across all paths. For this problem, it's going to be the union. For some other problems, it might be intersection. But that's what we're going to frequently do in data flow analysis. Any questions so far?
Yeah, I got one. So for D2, is there a reason, is there any reason you would need the bits of D0 and D1?
It's
Sorry,
yeah.
what I mean by that is actually, no, flip that around. So does D0 need a notion of what, like the definitions afterwards? Like, does D0 even need the bits?
Yeah, you're now talking about optimizing these things, but the only reason you can argue about this optimization is you kind of have all the data in front of you. You kind of get a feeling, right? It is. The thing is to make the algorithm systematic. You really don't, you want to have everything everywhere. Remember, right now you have the code without branches, backward branches. Imagine that would be a basic block here, right? Just imagine. And there is an edge like this.
Right, then that doesn't apply because D0 could follow that last block, right? Okay.
The analysis, you want it to be uniform. So before you see which branches go somewhere, yes, you could have make some optimizations knowing that something doesn't reach this point, but it's much easier to you to store the same length vector at each point of time. And it would make the manipulation easier because I can do unions and intersections between these vectors. If they're going to have different dimensionality, it would be a nightmare to manipulate.
All right, got it. Thanks.
Yeah. So you're right that in particular graph, you might optimize as a presentation, but for a general case, you can't, and it would make your life harder. Okay, let me just erase that, not to confuse anyone. Okay. Any questions here? Okay, that essentially relates to what you just said a little bit. And the question I have to you, based on the definition of reaching definitions that we had before, here is this piece of code, right? And there is a branch potentially here. And the question is, D2 reaches this point or not? So you see D2, it's right here.
Yes, because it's possible that D2 goes before you reach L2.
Yeah, this is goes back to Robert's question, essentially. So something can be much later than this in the code. It doesn't mean it cannot reach this point because I have backward edges, right? Okay, so you get a little bit of feeling of the problem. I make a short pause here because it's 2 p.m. And I think let's meet in roughly 9 minutes and we can go over applying this to some real problems. See you soon. Okay, guys, let's resume the class. Any questions so far? For people who had their cameras on before, if you can turn them back on, that would be helpful. Thank you. Okay, so we practiced a little bit to get a feeling of it. Let's try to make it more and more formal. So like you will see every step, we gradually get it more formal until everything becomes very mathy. So the first step is we talk about individual blocks. Let's look at the next abstraction we want to have. The next abstraction, I kind of want to abstract what happens within the basic block. We already figure out how to do it. I want to have a general way to say how things change depending when I go from between the different blocks. Essentially what I'm going to do is I'm going to define two fake nodes, one called entry node and one called exit node. They're just artificial nodes to simplify the analysis. We always have one entry point and one exit point from the code. Then I want to define essentially transfer functions that represent the information of the data flow that happens within the basic block. And that can be different depending what it is. So this is essentially a flow graph that I built on top of control graph. And I just set up a set of equations for all basic block using the notions of input and output for each basic block and transfer functions that represent the information of how the inputs change in these blocks to the outputs. So how it's going to look like. So each node, you're going to get an equations where we would say output equals some manipulations with input and transfer function. Or if there's a backward analysis, it can be the other way around. Input equals something from the output, right? So there are very simple transformations here. So each block has a transformation effect based on its statements. So it can change the input information it gets based on the statement it has here. And we had an effect when we had, for example, basic block 1 had an edge going into basic block 2. They had also trivial equations where input of 2 equals output of 1, right? So this is across this edge, right? Similarly across this edge. So those are the equations we're trying to get. So, and then the answer to the data flow problem is the solution to these equations. So we just write all these equations on what's happening right now in our code. And then the hope is the solutions to these equations give us the answer to the questions we want to ask. First of all, let's look at what the transfer function means. So imagine that the basic block B0 or whatever Bx has some information about uses or definitions or any other data flow problems. This is my input vector. Then every statement can change based on this definition, the information that comes from the input. So, and essentially the total transfer function, right, across the transfer of the information across the basic block is a step-by-step application of these individual transfer functions. So essentially the transfer statement called fs that's defined for the whole basic block, it abstracts out the propagation of the information in the basic block. For example, if we have a statement S of this form, X equals Y plus Z, and this is, definition D essentially, then the output of this statement, S stands for statement here, is a transfer function of S applied to its input. So each the statement has some input always, right? And then what we do, what this transfer does, it generates some new definitions that's defined as GNS. GNS is essentially definitions generated by this statement. And in this case, it's very trivial. It generates just one definition, D itself, right? So this is a very simple statement. It just had one definition generated. Also, it has a union of everything was given as a definition into it minus everything it's killed. So it means it's killed. It kills all the other definitions of X that reached this point before. So essentially, the transfer information of this statement with respect to reaching definition is gen union in minus kill, where gen is just one extra statement, right? It's just this def. And it's union of what it has as an input before minus what it's killed. And it can only kill any other definition of X from the rest of the program. One thing I want to highlight, the kills is non-selective. It doesn't care whether that X from the rest of the program can reach this point or not. It's very local. If it sees that X here is redefined, any other X with the rest of the program is killed in this place. Okay, is this clear? So this is essentially how the transfer function is defined. It's just a union of these two expressions. Okay, any questions? If there are no questions, then the next step is, how we combine those things. So we essentially had, right, transfer functions for D0, transfer function for D1, transfer function for D2. That's a local transfers. But what I want is the total transfer of the whole basic block. What I do, I formally define the output of the basic block being equal to the transfer of the whole basic block, which is just step-by-step transfer from, sorry, there's a typo here. So this should be D0. Sorry about this. So essentially, I just apply transfer one by one, and then what's the last transfer? The output is the output of the whole basic block. Okay, any questions here? So now we have a definitions of the overall transfer. Now, if we formally write the equations here, what that means is you start from the top, gen of D2 union, gen of D1, union, gen of D0, union, and then you get input minus kill D0, minus kill D1, and minus kill D2. That, using the mathematical equivalences and the set theory, I can keep simplifying this way, right? And at the end, what it becomes, it just becomes the gen B, which is locally exposed definitions, right? So gen B is all the definitions that reach the end of the basic block. So you see each step you add a gen, so every locally exposed definitions is available at the end of the basic block, right? Then you had kill B, a set of definitions killed by the basic block. So essentially everything that was redefined in the basic block would be killed in the basic block, right? It would be part of the kill B set. But that allows me to write the whole expression for the whole basic block instead of writing equations for each element, each statement of the basic block. Any questions here? Okay, let's experiment a little bit. So this is again, as a simple piece of the code as it could be, right? And we want to essentially write find a gen and kill set for it first. So remember that's a transfer function of a basic block. That's what it is. And there are incoming reaching definitions that are equal to outgoing reaching definitions. Each basic blocks generate definitions, which is a gen B set of locally available definitions. And there is a kill set. That's a set of all definitions in the rest of a program killed by definitions in B. And this is your equation, right? The main equation. What I want you to start with is to, before we go to this point, we first need to find gen and kill set. So let's try to do it together. So for simplicity, I'm just going to say basic block 1, B1. Right, then they're going to be B2. And then B3. And then we're going to have gen. And we're going to have kill. Okay, let's try to do it together. What would be the gen B of the basic block 1?
D0, D1, and D2.
Any other opinions? Thanks for your response. Any other opinions? Remember when we did a transfer, this defines D0. Yeah, so Zihan, you're right, but just the notion we're going to use, we're just going to say D1, D2. We're not going to write the statements themselves. That's why I had D1, D2, D3, right? So I think Dishan said D0, D1, D2. What's incorrect is D0. D0 is transferred from here to here, but then when it reaches this place, it's killed, right? Remember, only locally exposed definitions at the end of the blocks get into Gen B. Okay, these definitions.
Wouldn't D0 be part of the kill column then? I thought.
We will talk about that. Let's think about Gen first. So what we're saying, like what the Gen set would be here. And I think Zihan said x equal 10, y equal 11, which essentially means D1 and D2, and that's correct. I want to make sure everyone understands it. For simplicity, I'm going to just write 1 and 2, which stands for D1 and D2. Okay, then let's go to what Dishant asked, said, what is then the kill set of the basic block 1? Which definitions are killed by basic block 1?
D0.
Okay, 0. What else? Look at it formally. It says definitions. That's a definition in B minus QB. It says kill B is essentially a set of all definitions in the rest of the whole program that kill by definitions in B. Does it kill 0? That's correct. What else does it kill? So Al said 3 and 6. 3 and 6 are correct, but is it? So we already have 3, 4, 6. Anything else missing? There is one thing that's missing that's a little bit tricky, specifically in this example, to get you confused. There is one. Anyone? What else has got killed? Remember, that's a global view. So what happens here, you have to forget about the order. So what happens, because there are two statements, D0 and D2, each of this can kill the other one. So essentially, from the global point of view, D2 is also in the kill set because it kills by D0. That's just based on the definition because it kills it, right? It's gonna look at it globally. So it's 0, 2, 3, 4, 7, those the answer. And the gen set has 1 and 2. That's not a problem that something can be involved in gen and kill set because the way it's used is gen union input minus kill set. But remember, we shouldn't miss anything in the kill set because it might be required to properly be removed from the input set. And that's not a problem if it's removing, say, 2 from here because gen would add it back. Because if something in the generation set of that basic block, it's not going to go away. But formally speaking, that's their, the kill set. Having 2 or not in this case won't make a difference in the final result. But formally speaking, that's the right kill set. Okay, let's go a little bit faster. How about basic block 2? What is in their gen set now? And I want as many people as possible to participate. So, Robert, if you want to talk, you should mute yourself.
So gen will just be D3 and D4?
Yeah, so 3 and 4, right? And that's correct. How about kill set? Anyone wants to try?
So it's like D0, D1, D2, and then D6.
Hope my notation is clear. Sorry for my handwriting. But you're correct. 0, 1, 2, and 6, which stands for D0, D1, D2, and D6. That's correct. Thank you. Okay, let's do third block. Anyone wants to try? Anyone new? What is in the gen for this block? So someone asked why 3 and 4 are not killed in basic block 2. They don't kill themselves, and there is no other definition of X and Y to kill them in basic block 2. So if there would be another statement here, say X equals 10, then D3 would be in the kill set.
May I ask a question here?
Yes, go ahead.
So the definition of kill set is probably, in my point of view, any other same variable that's defined in the scope. So say you have a D0, Y equals 3, then other definition of Y should be killed, should be included in the kill set. Is this correct?
The other definition, yes, it should be in the kill set. So remember, kill and gen defined separately. It's possible for something being in both gen and kill set at the same time.
I see. But then I don't really understand why you would include the later expressions in the kill set. So like if you're looking at this control flow graph, D4 is never executed before D0.
The problem you have, you're trying to optimize and you look at the order. When we're going to do a data flow problems, everything looks like a vector. It doesn't know whether it's early or later. It really just manipulates the bits. There is no early or later or the order, right? So you're using information that you don't have in this analysis, right? Try to optimize it out. You're right that 2 in kill set in this case won't make a difference. But formally speaking, when you're going to write it, you're going to manipulate. What you're going to do, you're going to just take the whole block and take every statement one at a time and see everything it kills, right? And then you do union, right? That's it. That's what you're going to do. You're not going to go, oh my God, would it be this earlier or later? Wouldn't be that not really kill this or not, right? So that's what you're going to really implement. It's not optimal, but it is correct.
Well, I get it. Thank you very much.
So that first, there was a question, someone said, I think it was, who was that? I think Zihan said, you still didn't get why in B2 to get both gen and kill. Did you get it, Zihan, now or you didn't? Okay, sounds good. So any other questions? So we can move on. Okay, someone please do B3 for me. So gen should be very simple, right? 5 and 6, right? I hope everyone gets it by now. How about kill set here? That's easy. Come on, guys. Someone try. Robert? Yes, thank you. 1 and 3. So remember, I make as small example as possible to show all possible mistakes you can make, right? So it's essentially all possible really combinations in this little example. So revise it. So we get just gen and kill. We didn't really solve anything yet because what we want to get is this thing, right? Output gen in minus kill. But we will get to that soon. So this is just a sanity check. There's nothing special. I was just doing this exercise myself before showing it to you. Then let's look at how we're going to apply this moving forward. Remember, we just learned how to get gen and kill. We figure out how to do connect input and outputs. Then the question is, what happens if I had multiple inputs, right? So everything else is trivial. You already know input. You know how to do transfer, right? It's gen and kill and input, right? You already have the equations for that. That's a straightforward thing now for you. The only thing that left is what if I had a merge thing? This merge is called the meet operator. And for this problem, it's defined as a union of all the output, right? Because remember, this is a definition. If it's defined by one edge, we should treat it as possible being defined across other edge. So the input for this thing would be a union of output of F2 and an output of F3, right? So that's very simple. That's a join operator or meet operator. Remember, that's a generic operator. That operator union might mean different things in different cases, but in these cases, yeah. So it's just a bitwise union. Okay, let's experiment again. So let's get the same, or not the same, similar example. I think it might be slightly different. Don't remember. But I already give you gen and kill set. So we already painfully generated then gen and kill a few slides ago. So now what I want from you is to give me an out and input sets for each basic block. So there is the points of interest. So you don't generate. So what's interesting, what's happening here, what happens here, and what happens at the output of each of these blocks, and what happens at the merge. So this is the most interesting points in this graph because this is boring. There's no back edges here. So there's nothing interesting here. Everything is just zeros as the input, right? So the question is what we're gonna do here. So let's try. So remember the equations before, I wrote them in the previous slide. Your output is equal to gen, right? Does everyone remember still that, right? So the output of the basic blocks equals to gen of the basic block minus input minus kill of the basic block. So let me tell what would be the output on this edge, which is also the same as this edge. You need to do gen. So your input, remember, would be an empty set. Should be very easy, guys. Gen union empty set minus some kill set. So what is going to be the output here? Yes, so I'll write in the chat. This is just 1 and 2. Is this clear to everyone? It's a very easy equation, right? Gen B, which is just 1 and 2, union. And in the second part of the union is empty set minus something. You cannot make empty set any more empty. So it's just the empty set, right? So just 1 and 2. And so it is 1 and 2 here. Is this clear to everyone? I just apply their equations, this blue equation here, right? Gen union in minus Q. Okay, let's do something more interesting here. what would be their, sorry, what be the equation here? What would be the output of this block? Because remember, the output of this is the input of this, right? There's only one edge here. Output of this is the input of this. So it's easy, right? I'm interested in the output of this. Okay. Any questions? Okay, what's happened here? 3 and 4 I got, right? 3 and 4, and that's correct. And how about this thing here? Yes, that's correct. 2, 5, and 6. Any questions here? So this is correct, right? So you literally just apply those equations. There is no complications here. There are no back edges or anything. So this is relatively straightforward. Okay. Yeah. Okay. This is just my own notes. Okay. So things are a little bit more complicated, obviously, when you have a back edges, right? So when you have the back edges, the informations in the input can change. So what you just did, what I just did, together with your help, just converge in one step, right? But if I had a back edge, my input, after I make the full pass, might change because of this edge, and this merge might change. So there's always a question when this thing converge. And we're gonna formally define it probably in the next lecture, but just a hint for you, so it would converge, and it would depend on how many back edges, because only the back edges can change something as an input. And it means every time I went through this back edge, I might need to go through it again until things stabilize. So what I do, essentially, I do these equations multiple times until I get to the situation where between 2 iterations, there are no changes in the input and output. And that means I find a fixed point solution, right? And that means my algorithm converge. We're gonna later prove how quickly we converge. We can get guarantees on convergence. We're gonna prove all of that. But I hope you already intuitively see how the algorithm works, right? You just locally propagate the information, and I magically find all this information about all their, definitions across the whole program now. So after I can do that, I essentially can write an iterative algorithm, which I don't want to go formally right now. It's very, very simple, right? I just define the basic conditions. And then for each basic block, I literally do what we just did with you. For each input, I get a union of all the outputs that goes into it, all predecessors, right? For each basic block, I take what it gets. And then each output is equal to the transfer function, right, of that basic block, which is a gen union in minus q. And you keep doing this until there are no changes in the output. Okay, that's it. So if there are any change, then you need to keep doing it. So very simple algorithms, and we actually converge, and soon we're gonna, so we had advanced people here, so it's a fixed point in the lattice. I didn't define what the lattice is. Oh yes, but yes, you're gonna define it either today or beginning of the next lecture. But yeah, that's what it is. Okay, any other questions from anyone? Okay. So this is an upgraded version of the rich definition algorithm to make it a little bit more efficient. You can study it on your own. There's nothing super fancy here. This is how you can formally write all of this down. So Zihan said, is an input and output are the same? Input and output only the same if you had one edge. So output across the edge is the same as an input in this edge. But if this basic block has 2 inputs, you need to merge them, meet operator, right? If there's only one edge, then the output of the predecessor is the input of the successor. Does it answer your question, Zihan? Okay, so it's not always, but in most cases, if there's just only one input, right, then output is just the input. Yeah, merge input, well, So your input is a merge outputs of all the predecessors. That's exactly what it says here. You do union of all the predecessors for this basic block. So input is the merge output. Okay. So here, I specifically leave you another example on that would let you practice at home and get a feeling whether you understand the algorithm or not. It's a little bit more complicated, but just a tiny bit more complicated, right? Yeah, remember the previous example, just converging one step. There was no back edges, right? So there was nothing that could change, right? I'd make a pass through from top to bottom and we're done. In reality, it's depending on how many back edges, there may be more steps. So essentially here, I would give you the answers essentially. So you should try this example without looking at the answer and then see whether you merge it. So essentially here we have 4 basic blocks, right? So for this of these, and obviously exit block as a separate entry. So you had 7 statements. So the length of this vector is not surprisingly 7, right? And that's how it looks in the first and second pass. So you would have to do, surprise, surprise, kill set, gen set, write them down. And then using gen and kill set, you should be able to generate this set. For example, I'll just give you one example. For example, here, on the first iteration here, you're gonna get the gen set. The gen set is gonna have D1, D2, D3, because I, J, and A are all different, right? They're all into gen set. And so when you're gonna compute the output, all of this D1, D2, D3 will be ones, right? Because they are the gen set. And there is nothing else to kill because everything else is zeros, right? So that would be the output of your basic block. And then you do it for each of these blocks, you get these vectors. I really encourage you to try it out at home yourself, so you get a confidence on how it works and you can ask questions if you don't understand. But then remember the trick here, there is a back edge here, right? So at the beginning, when this is not defined, this is just an empty set. So the first time you do union, you just do union with an empty set, right? But when this goes here, here, and here, you go through this back, you go through this back edge, and the next time you come here, this is not 0 anymore, right? You're gonna have some meaningful information. That's gonna change this thing. So the second pass, as you can see, is different than the first pass, right? There is some difference in the bits here. But the third pass is gonna be identical, right? So that means your algorithms converge in just 2 iterations, which is not bad, right? If you think about it, it's essentially dependent on how many back edges you have. Okay, this is the example for you to practice. I give you a hint on how to do. Remember, you will need to write gen set, kill set, then write the equations for each, and then write int and output for each of this basic block. And then you would have to do 2 passes. First pass when you do the first forward pass for all the blocks, and then the second pass for the blocks where things change. For example, one thing you can notice, this edge only goes here. It means for this block, nothing changes in the second iteration because it doesn't get any new information coming, right? So this thing doesn't need any recomputation. It's identical, the same in and out. So only the things that get a new input is affected, right? Any questions here?
If you have multiple back edges that go to B2, would you treat those as a merge, or would you assume that you need more than 2 passes?
I didn't formally define how things converge. So for you, the only real, that's when I send you the number of back edges, just a hint, right? But reality, what you should do, you should keep repeating the algorithm until you don't see the difference, right? So for now, that's your stop point. Later on, we'll prove on how things change over the backward edges. There is the boundary that you can get, that you never need more than that number of iterations, but sometimes few iterations is enough. So your stop condition is no differences between 2 consecutive passes.
Oh, okay. So in this, formally, based on what you said, to confirm that the second pass is all you need, you would try it a third time, and
you just, I don't write it because it's identical to second.
Right. Okay. Got it.
Yeah. So that's a formal U condition. Later on, we're going to find the relationship between that and the number of back edges. But for now, it's just a hint so you can think about it. It's actually going to be very visible because after you're going to make a pass, right, you're going to see that since nothing changes, like you already have seen all the information over the back edges, if it doesn't bring any new information, nothing can change, right? So what you would need to have another back edge that you didn't see before, that something would change, right? Okay, hope that answers your question. So another example that we're going to do right now with you of another problem. Right now we did something called reaching definitions. So we were looking at all the definitions in different places of the code. That's not the only data flow problem that you would be interested in. In fact, there are tons of different data flow problems people want to ask. I'll just give you another example today. So you get a feeling that this is not like a pony that can only do one trick, that the data flow is the general approach, can solve a lot of different problems. And then we try to generalize it. So this other problem is a live variable analysis. A variable is called live at point P in the program if value of f is used along some path in the flow graph starting at P. So otherwise the variable is dead. So you see the difference with reaching definitions. Reaching definitions, we're asking whether this definition reached this point. Here we're asking whether the variable is live or not, so meaning it's useful or not, right? So the motivation for that is things like register location. You want to find things that are needed versus not needed, whether I can reuse the register or not. For example, if I know that the variable I is not live here, I can reuse it and use in another loop, right? So that's very helpful for register location. So I can save on the registers, which is a very limited precious resource. Okay, let's try to, so essentially the problem statement will be for each basic block, determine if each variable is live in each basic block, and size of the bit vector is 1 bit for each variable. So you get all the variables in your code, that's the length of your vector. Let's practice. So let's look at the graph on the right-hand side. Again, simple hammock. And I'm asking you whether V is live at a different points. So the first point is between D1 and D2. Is it live or not there? Is the definition of liveness clear?
I think V is live because Y equals V on the bottom right forms a path from D0.
Yes, exactly. You found the one path and that's enough. Okay, how about the place at the end of the basic block? Is V is live there?
Yeah.
Same reason. How about the entrance, or how about the basic block on the left?
I guess if there were no back edges, then yes. But sorry, then no. Because it isn't it isn't used in that block.
So you guys, you got to fill in, right? Here I went over the edge, over the over their edge in the graph, and out of a sudden it's not. Why? Because this path is not reachable for me. This is not reachable, that makes this not live. It means the V here is dead. And it's redefined with another V. So if there was something there here, it would be anyway dead. Because even here, it doesn't matter because it would be killed. Anyway, the point I'm trying to make is that you get an intuition on how V looks like. And now you're going to see that the algorithm you need to run for this would be actually different. So similarly to the previous thing, we need a definition of the transfer function. Remember, everything starts with a transfer function. The thing here that we would have to do tracing of the definitions in a backward fashion, right? Because here we look for uses, right? We want to go from the uses up to the defs, right? So if I had an execution path like def, and then use, that means that the way we identify the input is based on my output, not the other way around. So it's the data flow analysis, but input and output change their position. My input is defined based on my output. because really that use that is somewhere down the stream tells me whether it's useful or not. So for example, here you might have, output, A equals 4 and C equals 8, right? And there is another, so this is essentially the use, and that makes this thing live here, but B is not live here. So this thing that comes next is the one that defines the usefulness. Okay. So essentially that's my transfer function. But remember the transfer function we need, remember we had gen and kill set. Right now they're going to be similar sets, they just got slightly different names. The gen set is now called use, right? Which is a set of locally exposed uses. Before it was a set of locally exposed definitions. Now it's a set of locally exposed uses in B. So when we look at the basic block, we need to look at what is used, and use is my gen set. It's the one that makes something live, right? If something is a use and it's locally exposed use, it makes the variable live. And we want to propagate the incoming live variables. And before, remember, there was in minus kill. Now it's different because we're going backwards. So here we're going to take the output of the block and we're going to get minus all the definitions, because everything that's defined in between makes this not live anymore, right? Because it's really used this def, not this def, right? So use is the condition to be locally exposed, but if there's this def there that kills what was an input here. So def B is a set of variables defined in basic block, right? The set of all variables defined in basic block. You see, names are slightly different based on the specific problem, but the key idea is very, very similar, right? We had something that generates the data, right, just locally, and we had something that propagates the information from, in this case, from the output to the input in the backward direction, right? And then our transfer function, surprise, surprise, is input equals use of B union output minus definition, right? You see, equations are very similar, right? It's just the meaning of use and def slightly different, and input and output change their places. But everything else looks very similar. For a very different problem, we kind of get a very similar equations, right? Okay. So obviously you also need to figure out how to merge, right? So we also have a join, merge here. It just be joined based on the successors, right? So the meet operator is that if we look at the output of a layer, we merge, we merge all possible inputs into this layer, right? So that's exactly what it is. So essentially, you just merge the information, right?
So like if we are doing like a forward analyze, so our equation will be like the input will be in terms of the output of predecessors, and for backward analysis, our equation is like in terms of out to be the meet operator be ins. Is this the common way to do it?
Yeah, it's a common way, but things might change. Input and output can flip roles, and union can be different. Like you can have a union, or you can sometimes have intersection. Things might change, right? The general idea is the same, but the definition of the meet operator might be different. Input and output can flip roles, but everything else is identical. That helps define in a coherent mechanism later on to solve all these problems. Okay.
Okay.
For example, in this example, so I guess what I was planning you to ask, I guess I showed the answer, but we can hide it and try again. So what I want you first to do is use and def sets, right? So we already found the definition of use, which is a locally exposed uses. And so what I want you to find is on the basic block B1, B1, and similarly we want use and def. Sorry about that. Okay, anyone? So we want to do B1, B2, B3. So anything in the use set in the B1? Do we have any locally exposed uses in B1? Yeah, so Edgar said no, and that's correct. So it's an empty set here. How about definitions? Def set. Anything this thing kind of kills because it redefines it, right? It's def. Does it have any definitions? Any variable it kills?
A and B.
Exactly. I didn't notice who said that, but that was correct answer, A and B. Okay, let's look at the basic block B2. And anything in the use of their basic block B2? This is B2, sorry, I didn't. So this is B1, B2, B3.
B is being used.
Yes, B is being used. How about the defs? Anything killed in anything redefined in the basic block B2?
AC.
A and C. Hope others understand it. If you have questions, please ask. And basic block 3, can anyone else try to do it so we make sure that everyone understands? So what we have as a use?
A and D.
How about D? Are you sure about D? What's the problem with D?
D is previously defined in the same block and not before.
Yeah. So it's not a locally exposed use because it's just locally consumed. So no, it's just A. How about def? So does it redefine anything? Anyone? Just look at these things.
Both B and D are defined.
That's correct. So it's not that complicated. So I'm just trying to give you a sense of it. It's just B and D. Okay. It's using def, and using them, we can just write our equations relatively simple. Then that's an algorithm for liveness, which essentially there's a boundary condition, there's an initialization, all empty sets. And then the output is the union of all inputs for all successes. And the input is defined as a transfer function of the output, which is use union out minus def, right? And then similarly to the previous thing, I leave you an example with 2 passes, right? That would converge in just 2 steps. So this is just, one basic block more to make it a little bit more complicated and has a back edge. So you can practice at home, right? And if something doesn't work for you or mismatches the result, then you can come back and ask questions, okay? But that would help you to practice at home because eventually you're going to implement this algorithm. Not that, but a general algorithm. So you want to get a sense of how it works. Because if you don't make your hands dirty, it would be hard to implement it. Pretty much what I want to finish this lecture today, because I don't want to start a new big piece of material, is that we look at 2 big problems. One is called reaching definitions, and one is called live variables. And if you start to look at that, you're going to see there's a lot of similarity in how we solve them. They had a domain, the set of elements on which they defined. Here they were defined in definitions, here on variables. It look very similar, it's a vector operations. In one case, we had a forward propagation of the information. Output was defined based on the input. And here the input was just, a union of all the output. And here was the same thing. This is just a transfer function symbol, right? This is a meet operator symbol. And in both cases, it was union. So this thing was really union here. And that was the transfer function within the basic block. And that was the boundary conditions and initial conditions. So you see, I was solving two different problems, but the setup is very, very similar. So that, you know, creates an intuition there can be a lot of other similar problems, for example, available expressions that might look very similar, but just some equations look slightly different. And then if I want to solve all these problems, I probably don't want to write a solution and the code for each of that. I want to write a solution for all of them all together and then use this general framework to solve all these different data flow problems. And that's what we're gonna do in the, you know, the next lecture, next week. Any questions? Okay, I hope there were no questions. In general, please, if I go too fast, I try to be relatively slow and do a lot of exercises by hand. So in the first real big lecture, that you get a feeling. In the future classes, I will go a little bit faster. So if it's too fast, you should let me know. And also, please do the exercises I mentioned, right? Like after the class, everything will be shared with you. You're gonna see all the examples. So please don't ignore and practice, because that's the only way you can make and learn the material deeper, right? I cannot go every example in the class, but I hope you will do it at home. Okay, if there are no questions, then thanks everyone. And I hope to see you in a week, and hope you have a good progress and, you know, had a good experience of with LLVM and Bojan in tutorials. Thank you, guys. Thank you. Bye.